A few months ago, I met an executive from a major solar firm who described his daily work as a slow-motion car crash. He told me about these bidding wars where the prices for high-efficiency panels had just plummeted, down to 0.6 RMB per watt, which is essentially the price of a cheap soda. He looked absolutely exhausted, and he pointed to this stack of contracts on his desk that he called suicide notes. In his eyes, the industry wasn't just competing, it was engaged in this collective act of self-destruction, a race to see who could go bankrupt last. But as we step into the first day of 2026, that whole atmosphere of desperation has been replaced by something far more clinical. The suicidal bidding rooms have gone quiet. They've been replaced by a new, rigid price guidance mechanism from the NEA that effectively outlawed that race to the bottom. It was an instantaneous shift from a market that valued nothing but scale to one suddenly forced to prioritize value and longevity. What's truly striking, however, isn't just the price floor on Earth. It's where that ambition has been redirected. While the industry was bleeding out in 2025, a massive pre-research project was being finalized, the space-based solar power plan. And we aren't just talking about more panels on rooftops here. We are talking about a kilometer-wide array sitting 36,000 kilometers above our heads, catching sunlight that never sets and beaming it back down via microwaves. It is a staggering contradiction. Just a year ago, these companies couldn't afford to keep the lights on in their own factories. Now they are the primary architects of a celestial energy grid that aims to bypass the atmosphere entirely. It makes you wonder, was the brutal involution of the last 2 years a sign of a failing industry, or was it the necessary painful shedding of skin before the leap into the final frontier?
It's the ultimate pivot, isn't it? It's just a stunning strategic move.
It really is.
You have a government needing to enforce stability in this wildly successful but at the same time, financially ruinous terrestrial industry.
Right.
And at the exact same moment, they're committing resources to a decades-long, multi-billion-dollar infrastructure project in geostationary orbit.
So for our deep dive today, we have to unpack that strategic paradox.
That's the mission. We're going to analyze the immediate, sharp, domestic regulatory restructuring. I mean, how they managed to stop those brutal price wars literally overnight.
And then connect that to the big picture.
And then trace the ambitious technical roadmap for space-based solar power, or SPSP. We'll look at the necessary infrastructure, the precise technology they're developing, and the massive geopolitical and economic stakes that are driving this dual approach.
Okay, let's unpack this. And we have to start with the mess on the ground, because that's the context for everything that comes after. Those contracts, the suicide notes. This wasn't just healthy capitalistic competition, it was something else, this involution you mentioned.
That concept of involution is absolutely critical to understanding the pivot.
Okay.
In the context of the solar industry, it describes this state of hyper-competition where the inputs, the labor, the capital, the sheer effort, they just increase dramatically.
But the output value?
The output value remains stagnant or even declines. So you have tremendous success in terms of manufacturing capacity and scale, yet zero marginal return.
And when prices drop to 0.6 RMB per watt, as they did in 2025?
The margin just evaporates. It's gone. This isn't a natural market correction. This is a collective act of self-destruction. Every company is forced to just pump up the volume to cover fixed costs, which drives prices down even further until everyone is facing widespread financial distress.
It sounds like it threatens to bankrupt the very industrial base that made them a global solar powerhouse in the first place.
That's exactly what was happening.
So the industry was basically drowning in its own success?
A perfect way to put it.
They had massive scale, but that scale was leading to financial toxicity. What exactly made 0.6 RMB per watt so unsustainable? I mean, are we talking it's below the cost of the raw polysilicon? Or?
Oh, it was certainly below a sustainable margin, even with the vertical integration advantages that a lot of the big firms have.
Wow.
At that level, you are barely covering the costs of raw materials. Things like polysilicon, glass, the aluminum framing, let alone the highly specific electricity required for crystalline growth and cell processing.
And forget about R&D.
Forget about R&D, maintenance, or capital expenditure for new equipment. It's all out the window. And the sources show this led to huge inventory buildups, factory utilization rates just dropping off a cliff. Even major players were facing existential liquidity crises.
Because all the profits were sucked out of the system.
Exactly. All in the name of winning the next massive government or utility contract, no matter the price.
That paints a picture of, well, unnecessary forced intervention. So how immediate and targeted was this regulatory pivot that shifted them away from this quantity at all costs mindset?
Yeah.
And importantly, who led it?
It was an immediate, comprehensive response.
Yeah.
Very targeted towards stabilizing the 2026 market. And it was spearheaded by the Ministry of Industry and Information Technology, or MIT.
MIT.
Yeah, in conjunction with the National Energy Administration, the NEA, MIT explicitly designated 2026 as a crucial period for strengthening governance in the photovoltaic sector. This wasn't some general guideline. It was a firm policy designed to stop the bleeding.
So the leadership recognized that if they wanted their top firms to survive to build the celestial infrastructure, they first had to stop them from committing financial suicide on Earth.
That's the logic, 100%.
When you say they used market and legal measures, what does that actually mean? What specific mechanisms were put in place? Did they literally just impose a price floor?
They used a highly structured set of tools,
Yeah.
mostly aimed at quality control and capacity restriction. So one of the primary measures was improving price monitoring and imposing implicit price guidance, to prevent illegal dumping and the kind of predatory pricing that just drags everyone else down.
But what was the main lever?
The most significant measure was using quality standards as that lever. They announced they would use market and legal measures to systematically phase out outdated production capacity.
Ah, that's the key, isn't it? It means any factory that is only capable of producing cheap, low-efficiency panels is suddenly no longer protected or viable.
Precisely. To survive and expand, companies now had to meet higher standards for conversion efficiency and product longevity. This forces companies to pivot capital into genuine technological innovation.
So, by strengthening product quality oversight,
they automatically make the low-margin, high-volume strategy non-viable. This strategy ensures a better, healthier balance between supply and demand, stabilizing prices, and allowing the leading enterprises to actually become sustainably profitable.
which is a necessary financial prerequisite for undertaking, multi-billion-dollar R&D later on. It's the absolute foundation for it.
So success is no longer measured by the sheer number of cheap panels you can churn out, but by efficiency and technological sophistication. What specific technologies are they implicitly prioritizing as part of this shift to value?
They are channeling capital into high-efficiency, next-generation cell architectures. Specifically, we're talking about technologies like heterojunction, or HJT,
HJT, right?
and tunnel oxide passivated contact, or TopCon cells. These technologies offer conversion efficiencies that are significantly higher than the older PERC technology.
Now, for the domestic industry, pivoting to value means mastering these more complex, higher cost, but ultimately higher margin products.
Yes, the push for innovation-driven development is a mandate to keep technological leadership. It's about moving beyond mere manufacturing scale to genuine technological advantage.
And this strategic stabilization has a critical global dimension too. By ensuring quality and higher prices domestically, does this also change their positioning in international markets? It absolutely does. The fifth key task they outlined was promoting deeper international cooperation.
Okay, how so?
Well, historically, the output of that involutionary price war often resulted in accusations of dumping low price, sometimes lower quality panels onto global markets. That created a lot of trade friction.
I can imagine.
So by enforcing high quality and ensuring domestic companies are profitably pursuing high-value tech like HJT and TopCon, they can use this reformed, higher quality capacity globally. Not by undercutting foreign competitors with unsustainably low prices, but by competing on superior performance and durability.
It's about commanding the high ground in the future energy transition.
That's the long game.
It's a remarkable piece of strategic engineering. They are deliberately killing off the financially draining, low-margin competition to force capital and talent into the higher-value, R&D-intensive areas, which just happens to set the necessary foundation for the space initiative.
You've got it. The stabilization on Earth wasn't the end goal. It was simply the process of monetizing the domestic industry so it could afford the multi-billion-dollar R&D required for the Celestial project.
That's the perfect transition. You can't launch a kilometer-wide solar array into space if the companies tasked with designing the high-efficiency components are bankrupt.
Exactly. This enforced maturation process prepares them financially and technically. But the question remains, why is terrestrial solar, even high-efficiency TopCon solar, suddenly deemed insufficient? Why the need to leap 36,000 kilometers above the atmosphere?
Which brings us to Section 2, the cosmic necessity.
And it's rooted in the long-term, high-stakes background of national and global climate commitments.
Right, the big picture.
The official, very public commitment is to peak CO2 emissions before 2030 and achieve carbon neutrality before 2060. These are ambitious, hard targets that require truly staggering amounts of non-fossil fuel energy generation.
And climate change is viewed as a definitive global challenge.
Where achieving net zero is an urgent and, really, a non-negotiable goal that requires disruptive technology.
That's a staggering amount of energy required. And current ground-based renewables, even if they're stabilized and highly efficient, they still have their limits, right? We're talking about the intermittency problem.
Intermittency is the Achilles heel of terrestrial renewables. It just is. Wind doesn't always blow, and ground solar is fundamentally limited by the day-night cycle and atmospheric interference like cloud cover.
So if you build enough solar panels to power a city during the day, you have zero power at night.
And that necessitates enormous, expensive battery storage, or you end up relying on fossil fuel backup like natural gas peaker plants, which just defeats the whole purpose of net zero.
The sources are pretty clear on this.
They are. They state that current intermittent technologies are not able to meet the challenges of this scale of decarbonization because they can't provide baseload power.
So the urgent need is for a clean energy source that is sustainable, affordable, secure, scalable, and non-intermittent. That's the definition of baseload power.
Exactly. And that is precisely the fundamental advantage of space-based solar power. The goal is constant, uninterrupted power generation.
And in geostationary Earth orbit, or GEO, where these arrays are planned to sit.
The solar radiation intensity is substantially higher. We're talking around 1,361 watts per square meter compared to, typically under 1,000 at the Earth's surface peak.
But more importantly,
more critically, the station bypasses atmospheric filtering, and because of its orbit, the sun never sets on the collector arrays. The energy source is available 24 hours a day, 365 days a year.
That non-intermittency means the GEO station can act as a true baseload utility, always on, always generating, regardless of weather or time of day. But let's get into the mechanics. You collect the sunlight 36,000 kilometers up. How does that energy get down to the terrestrial grid without massive loss?
The process involved a highly complex, multi-stage conversion and transmission chain.
Okay, break it down for us.
First, the massive orbital arrays capture the solar energy and convert it to DC electricity. This is done with advanced high-power solar cells designed for the vacuum and temperature extremes of space.
Step 1.
Second, the DC electricity is transformed into radio frequencies, specifically optimized microwaves, or possibly lasers, by a massive transmitting antenna, which has to be held in precise alignment.
Step 2. Then you beam it down.
Third, the microwave or laser beam is transmitted 36,000 kilometers down to Earth. And fourth, on the ground, a huge receiving station called a rectifying antenna, captures this beamed energy.
And that turns it back into usable power.
It converts it back to DC, then to AC power, and integrates it directly into the power grid.
I imagine the efficiency of that whole chain is the biggest technical challenge. I mean, every step from the solar cell in space to the power plant on the ground has to be incredibly optimized to make this economical.
That is precisely the core challenge. The success of SPSP hinges entirely on achieving unprecedented levels of efficiency in high-power wireless transmission. The system has to be robust enough to handle the 2047 power flow and precise enough to aim a beam over a 36,000-kilometer distance without any drift.
Which is why the institutional commitment has been so sustained. It shows they view this as a solvable problem.
Absolutely.
Tell me more about that long-term institutional support. This isn't some quick fix they dreamt up in 2026. This is clearly part of a strategic long-view plan.
It speaks volumes about the level of strategic planning involved. The China National Space Administration, or CNSA, has supported SPSP system and Q technology research since as early as 2008.
2008, wow.
Yeah. And this long-term focus has been consistently reinforced by the National Natural Science Foundation of China, the NSFC, which has supported fundamental foundational research in this area since 2015. This is the hallmark of a national strategic project embedded deeply within successive five-year plans.
Which ensures resources and political will remain focused regardless of any immediate economic turbulence.
That's right.
And we have tangible evidence of this commitment on the ground. They're already testing these concepts before launching anything large. The Space Solar Power Experiment Base in Chongqing stands out.
Yes. The Chongqing base, established in December 2018 with an investment exceeding $15 million, is the crucial terrestrial testbed.
And what's the focus there?
It focuses on tackling the major technological bottlenecks necessary for orbital realization. The core research fields are, first, microwave power transmission, MPT.
Right.
Second, laser power transmission, LPT. Third, the high-voltage electric technology required for the kilometer-scale arrays. And fourth, studying the environmental safety and biological effects of high-power wireless power transmission.
So they're trying to prove the entire theoretical energy chain works before they commit to the monumental task of orbital construction.
That's the critical link. They are testing the feasibility of beaming power down safely and efficiently before they try to build anything city-sized in GEO.
Okay, let's move into Section 3 then, the technical blueprint and roadmap. This details the path from a 1 kilobariwig ground demo to a 2 GW celestial utility. And we have to start with the initial ground demonstration breakthroughs, the ZURI project.
The ZURI, or Chase the Sun project, is where the theory met the lab. It started alongside the Chongqing base establishment in December 2018. It was designed to validate a specific concept called SSPS omega, which had been in development since 2014.
So it's a full system ground experimental demonstration.
Exactly.
What was the technological chain they were trying to prove with ZURI?
They needed to prove the seamless integration of the entire energy chain. Concentrated sunlight collection, conversion to DC power, conversion to microwave frequency, transmission to the beam, and then conversion back to usable DC power at the receiver end. The whole goal was to demonstrate that all these different complex technological elements could work cohesively within one system architecture.
And what were the early achievements in terms of power and distance?
The initial ground transmission demonstration achieved power delivery over a 100-meter distance.
Which is short, but...
It's short, but it's meaningful for a laboratory test. The output GC power achieved was 1 kilowatt, with an initial goal of reaching 20% DC to DC transmission efficiency across the entire system.
So while 1 kilowatt over 100 meters seems tiny compared to the 2 GW goal 36,000 kilometers away.
It proves the critical concept. It proves that the phased array antenna works, the conversion elements are stable, and the rectenna can capture the beamed energy. It validates the foundational physics needed for the massive scale-up.
That cleared a necessary technological hurdle. Now, looking at the core technologies, the wireless transmission method is still the biggest variable. Which major institutions, CAST, Zhejiang University, Chongqing University, are leading the charge? And what are the specific challenges they face with microwave power transmission, MPT?
MPT is currently being studied as the most important primary transmission technology, mainly because microwaves can penetrate cloud cover more effectively than lasers.
Right, which is critical for baseload power.
Exactly. So CASIS, the China Academy of Space Technology, and other leading universities are focusing on several major engineering challenges. First is the sheer scale of the phased array antenna in space. For 2 GW of power, you need an antenna measured in kilometers.
Kilometers.
That demands ultra-lightweight materials and complex thermal management systems, as the antenna itself will be absorbing and dissipating immense heat.
That scale introduces a level of complexity that we haven't even seen in the International Space Station, which is comparatively tiny. A kilometer-wide antenna has to maintain alignment perfectly over 36,000 kilometers.
And that leads to the second major challenge: beam pointing precision and control. The antenna must maintain a precision of microradians over that vast distance.
How is that even possible?
It has to compensate for any subtle gravitational shifts, orbital perturbations, and thermal expansion of the kilometer-scale structure. They rely on advanced, self-correcting phased array electronics to ensure the beam remains focused on the ground rectenna and doesn't drift.
And what about the receiving end on Earth, the rectenna? If we're talking about beaming gigawatts of power, that ground station must be enormous, which leads to significant land use issues.
Exactly. That's the third major practical challenge. Microwave beams spread as they travel, so the receiving rectenna needs to be very large to capture the majority of the energy. Estimates for a 2 GW station require a rectenna field spanning several square kilometers.
So the efficient, safe, and environmentally sound use of that much land for a single power station is a significant consideration.
A huge one, especially near population centers or sensitive ecosystems.
Okay, so contrast that with laser power transmission, or LPT.
Yeah.
Why is that still being pursued if MPT seems to be the primary focus?
LPT is still under intense study, especially by institutions like the Beijing Institute of Technology. It's mainly for flexible, long-distance power transmission for specialized lower power applications.
And the beam is more focused.
Highly focused, often only a few meters wide, which means the ground receiver is much smaller, and that solves the land use problem associated with MPT. However, LPT's major drawback is its severe degradation by atmospheric conditions.
Like clouds?
Clouds, fog, Even heavy rain can absorb or scatter the laser beam, rendering it intermittent, which, defeats the core purpose of baseload power generation. It also raises higher safety concerns regarding accidental beam exposure.
It sounds like MPT is really the only viable path for that 247 baseload utility goal.
For now, it seems to be.
So let's move to the revised multi-stage roadmap, which provides the actual escalating schedule. This is a fascinating look at how they plan to bridge the gap from a 1 kilowatt lab demo to commercial scale by 2050.
This roadmap is the strategic spine of the entire project. It breaks the monumental task into 4 manageable, though still highly ambitious phases. It's designed to validate technology, scale, and assembly complexity sequentially.
Let's start with phase 1, which begins almost immediately around 2026. This is the LEO demonstration. What are the modest but crucial technological goals here?
The mission character is a high-power electric generation and wireless power transmission demonstration in low Earth orbit. The goal is validation, not power delivery. We're talking about a very small scale. 10 kilowatt low level power, operating at a relatively low voltage of 500 V.
And the antenna.
The MPT antenna size is measured in meters, and the transmission distance is short, 400 kilometers in LEO.
Why LEO first at such low power?
EO offers an accessible, low-risk environment to test the critical long-distance beam control precision. They are validating the ability to aim and maintain the beam between space and ground, and testing how different solar array types, specifically thin film and concentrator arrays, perform over time in the specific thermal cycling and radiation environment of LEO.
And the power density on the ground is low for safety.
Extremely cautious. The target microwave density on the ground is set at just 30 microwatts per square meter. This is far below any regulatory limit, confirming the mission is purely for measurement, tracking, and alignment validation.
That makes sense. LEO is the proving ground. Phase 2, around 2030, is the massive leap into geostationary orbit, GEO. That's where the real complexity begins.
This is the GEO high-power WPT demonstration mission, and the specs jump significantly to reflect the true challenge. Power scales up to 500 kilowatters with a voltage around 2 kV.
And the antenna in distance.
The MPT antenna scales up to about 10 meters, and the transmission distance jumps to the full 36,000 kilometers. This mission is all about proving that 36,000 kilometer beam propagation and control is viable for sustained power delivery.
And what does this require in terms of infrastructure and logistics compared to the LEO demo?
This is where assembly starts becoming a critical necessity. Modules for this 500 kilowatt satellite must be launched to LEO first, undergo simple assembly or integration there, and then be transferred using dedicated orbital vehicles up to GEO for the final demonstration.
So it's testing the in-space logistics chain.
Exactly. The one that's necessary for all the subsequent larger systems.
Then phase 3, around 2035, is the critical transition point, the first true megawatt pilot system.
Yes, the MW Pilot Space Solar Power Project. This is where engineering moves from demonstration to large-scale construction. Power scales dramatically to 20 mW with a 5 kV voltage level.
And the antenna size.
It jumps again to a 100-meter scale, the size of a modest football stadium. This phase demands complex assembly operations required in GEO, utilizing advanced robotic operators.
And that complexity involves what?
Connecting and managing 100-meter scale segments while maintaining alignment and power routing. It's about preparing the teams and the technology for the final monumental leap.
And finally, the colossal goal, phase 4 around 2050, the full commercial scale gigawatt space solar power system, 2 gigawatts.
This is the ultimate objective, the kilometer scale utility in orbit. The target power output is 2 GW, operating at a high 20 kV voltage level for efficient power handling. The MPT antenna scales to the kilometer size, which is indeed the small city in orbit you mentioned in the opening.
And the complexity of assembly
becomes extreme. It requires sophisticated ultra-large platforms and potentially the introduction of actual component manufacture in GEO itself.
You mean using orbital resources or highly automated fabrication to reduce the incredible launch mass required?
That's the idea.
A kilometer-scale antenna operating at 20 kV, 36,000 kilometers away? That's a monumental engineering leap that requires not just better components, but entirely new capabilities.
It does.
This brings us squarely to Section 4. The infrastructure required and the high geopolitical stakes driving this whole effort.
That's right. The ambition of that roadmap demands a logistical network that fundamentally redefines space travel. To put a 2 GW station, which is physically massive, into GEO requires unprecedented launch and assembly capability.
Let's start with the heavy lift requirement. How does the required launch capacity for the 2050 goal compare to existing capabilities?
It necessitates a completely new generation of reusable heavy launchers. For the 2030 goals alone, they require rockets capable of launching payloads of 50 metric tons or more to LEO.
And for the 2050 goal?
For the ultimate 2050 goals, the requirement escalates to over 100 metric tons to LEO.
To put that in perspective,
the maximum payload of the current, highly capable Long March 5 is about 25 tons to LEO, and the American Falcon Heavy can lift about 64 tons. The 100-ton requirement represents a step change in engineering. It is the scale of the Long March 9, which is currently under intensive development.
It's not just the mass either, is it? It's the sheer physical size of the components being launched. They have to be able to launch large, partially assembled modules.
Absolutely. The size of the payload fairing, the protective shell, is equally demanding. For the largest missions needed for the 2050 scale, the envelope size must be 10 meters or more in diameter and 25 meters or more in height.
And that's crucial because
it allows the launch of large prefabricated structural units and antenna segments, which minimizes the amount of fiddly assembly required in the extreme environment of GEO. This is logistics at the highest level. The rocket determines what you could build.
The launch vehicle is only the delivery truck, though. Once the components are up there, the entire kilometer-long structure needs to be put together, often far from Earth. What does the roadmap specify for in-space assembly?
The demands shift based on complexity and distance. For the early 2030 missions, assembly is simpler and happens in LEO, using robotic arms. But for the MW and GW systems 2035 and 2050, the assembly site must be geostationary orbit.
And performing complex robotic assembly 36,000 kilometers away presents massive challenges. The communication latency.
That's the big one.
That's wild. Operating a robot in GEO means a significant time delay in communications. How can they manage assembly with that latency?
It means the assembly robots cannot be purely teleoperated from Earth. They have to possess a high degree of autonomy.
So they need to think for themselves.
Capable of complex decision-making, object recognition, error correction, and self-diagnosis with minimal instruction from ground control. The structural materials themselves also must be designed for autonomous self-healing and long-term stability in the harsh GEO environment, managing extreme thermal expansion and radiation damage over decades.
So you need a revolution in space, robotics, and material science happening at the same time as the heavy lift development.
All at once. It's a system of systems.
And what about moving components between LEO and GEO? If you can't launch everything directly to GEO affordably, you need internal orbital transport.
You need highly efficient, reusable orbital transfer vehicles, or OTVs. These vehicles are critical for moving modules, supplies, and potentially maintenance crews from LEO staging areas, where the heavy lift rockets drop their payload up to GEO.
And the key requirement there is efficiency.
It's efficient, high-power electric propulsion. It provides extremely high specific impulse or fuel efficiency compared to traditional chemical rockets, even if the trip takes longer.
What power levels are required for these necessary orbital transfer vehicles?
The roadmap specifies substantial power requirements for these OTVs, starting at over 400 kilowatt power levels for the earlier stages and escalating to over 1 millibobu for the later phases, leading to the 2GW station.
And that necessitates
the development and mastery of high-power electric propulsion systems, like advanced Hall thrusters or plasma propulsion, which again is a huge technological undertaking in itself. This logistics network, the heavy lift, the OTVs, the autonomous assembly, is as vital as the SPSP system itself.
This moves us beyond a mere energy project. This is a foundational strategic space infrastructure undertaking. Let's connect this to the broader context. The pursuit of comprehensive national power, or CNP. Why is SPSP central to that goal?
The space program and projects like SPSP are identified explicitly as a key component of the goal of national rejuvenation and accumulating comprehensive national power, which is defined by economic, military, and technological strength.
So the logic is that technological dominance in key frontier areas like space energy generation translates directly into long-term economic superiority and national security resilience.
That's the idea. Technological innovation isn't just a byproduct, it's the primary engine of national strategy.
And it's underpinned by high-level leadership support.
Exactly. The consistent emphasis has been that the country cannot lag in the competitive arena of science and technology. The structure supporting this is consistent, long-term prioritization via the 5-year plans, which mandate goals far beyond typical Western political cycles, guaranteeing resources for projects that span decades. And this entire ecosystem is reinforced by the policy of military-civil fusion.
Military-civil fusion is perhaps the most strategic element here. How does a massive, ostensibly civilian energy project like SPSP intersect with military objectives, according to the sources? What is the dual-use potential?
The dual-use potential is significant, which makes the SPSP endeavor inherently strategic. The technology being developed, specifically high-power, precision microwave transmission and high-voltage power management in space, has immediate strategic applications.
Can you give me some concrete examples of those applications?
Sure. First, military analysts recognize that solar power generation, including SPSP, is a viable source for battlefield energy needs.
So powering remote forward operating bases.
Exactly. Or other military facilities without relying on vulnerable, long supply lines for traditional fuel generators.
And the second application?
The same phased array antenna technology, designed to beam power efficiently to a rectangle on Earth, can be adapted for high-power directed energy applications. The ability to precisely aim a high-intensity microwave beam across 36,000 kilometers involves physics and engineering transferable to advanced satellite communications, electronic warfare, or even future space-based defensive systems.
And the ground infrastructure supports this duality, right? We mentioned the Chongqing base earlier.
We did. The experimental base in Chongqing explicitly involves the Chongqing Military Civil Fusion and Innovation Research Institute. This confirms that the R&D is consciously engineered to serve both high-power civilian grid demands and strategic defense applications, ensuring maximum utility for the national investment. The technological output serves the grid, but the underlying capability serves the state's comprehensive national power.
Now, let's pivot to the ultimate economic and political vision tied to this strategic investment. The long-term forecast mentioned in the opening was simply staggering: a $10 trillion annual return. What is the scope of that vision?
The long-term economic goal is truly audacious. It's tied to the proposal to establish a cislunar space economic zone by 2045.
Cislunar, so Earth, Moon, space.
Yes. This zone includes resource exploration, space manufacturing, and critically orbital power generation. The estimate, often cited by directors of space agencies, is that this exploitation of cislunar space could generate an annual return of more than $10 trillion.
Hold on a second. $10 trillion annually is a number so large it's difficult to grasp. It's roughly 10% of the entire projected global economy by that time. Is that estimate credible? Or is that primarily an advocacy figure designed to secure funding and buy-in for this maximalist approach?
That is the right question to ask. The sources are highly skeptical about the validity of the $10 trillion estimate.
So it's more of an advocacy effort.
It functions more that way. To reach that figure, you have to make several heroic assumptions. Perfect technological success in SPSP with high transmission efficiency, extremely low launch costs achieved by the Long March 9, and ignoring the massive upfront capital investment, which would run into the hundreds of billions, if not trillions, of dollars.
So it's a compelling future narrative.
Used to justify the enormous cost and risk associated with the project during critical planning debates, especially ahead of new 5-year plan budgetary allocations.
So it's less a realistic market projection and more a political declaration of intent. We believe the economic future is in space, and we intend to dominate it.
That's a good way to read it.
Beyond the economics, what role does this SPSP initiative play in China's global diplomatic narrative?
Diplomatically, the SPSP goal is used to support the narrative of building a community of shared future. This narrative emphasizes the peaceful use of space and actively seeks to increase the participation of developing countries in space infrastructure projects, positioning the nation as a technological mentor and a benevolent global partner.
How does developing this massive strategic technology align with the principle of global benevolence?
By focusing on a technology that provides non-intermittent clean energy, they frame it as a solution to global energy poverty and climate change. This aligns perfectly with the objectives of the Outer Space Treaty, which promotes peaceful use.
So they use this narrative to shape international governance debates,
emphasizing that the exploration and use of outer space should be for the benefit of all countries. This strategy increases international prestige and provides a valuable counter-narrative to geopolitical competitors who might portray their space activities as purely aggressive or closed off.
That brings us full circle. We've traced the photovoltaic industry's journey from domestic financial self-destruction in 2025, stabilized by radical government-led reorganization in 2026, forcing quality and profitability, to the breathtaking, decades-long technological pursuit of space-based solar power. A pursuit requiring 100-ton lift capabilities, autonomous GEO construction, and the mastery of wireless power beaming over 36,000 kilometers.
The entire strategic arc demonstrates an incredible clarity of purpose. The financial pain on Earth was not just a crisis, it was the necessary catalyst. By enforcing quality and profitability domestically, the strategic decision was made to shed painful low-margin competition while simultaneously leapfrogging competitors entirely into a high-value, high-risk space domain.
And the goal is not merely cheap energy.
No, it's constant, scalable, baseload power generation supporting core national goals of technological dominance, energy security, and national rejuvenation, all secured far above the atmosphere.
The pivot from cutthroat price wars over cheap terrestrial panels to designing orbital power stations the size of small city structures requiring autonomous GEO manufacturing and heavy launchers that don't even exist yet demonstrates the extraordinary lengths to which nations will go to secure continuous, non-intermittent clean energy, radically shifting the very definition of solar power from a rooftop fixture to a celestial utility.